When we look up at the night sky, what do we see? A vast, seemingly endless expanse of stars, galaxies, and cosmic dust. We see a universe so immense that it's difficult to comprehend its scale, filled with phenomena that challenge our understanding of space and time. But what if the universe isn't as infinite as it seems? What if, in reality, we're living inside a gigantic bubble, one that contains everything we know, from galaxies to black holes, in a finite and closed system? This idea might sound strange, even far-fetched, but the possibility that we could be living inside a cosmic bubble is one of the most fascinating and radical concepts in modern cosmology. While traditional theories of the universe have placed us at the center of a vast, infinite cosmos, the notion that we could reside inside a giant bubble offers a completely new way of thinking about space and reality. If true, this theory could radically alter everything we know about the universe, from its origins to its ultimate fate. In this chapter, we will explore this concept and set the stage for the discussion to come. Could we be living inside a giant cosmic bubble? Could space itself be a closed system, one that's not infinite but contained within a vast and potentially infinite set of other bubbles, each with its own laws of physics? And if we are inside a bubble, what does that mean for the nature of the universe itself? Is this bubble just one of countless others in a multiverse, or is our bubble the only one in existence? Let's dive into this idea, one that challenges the core of modern cosmology. We'll take a closer look at how the concept of a cosmic bubble fits into current theories about space-time, cosmic inflation, and the observable universe. We'll explore what it means for our understanding of the universe's structure, its boundaries, and its ultimate fate. But most importantly, we'll consider how this theory could change everything we think we know about space itself. The traditional view: an infinite universe. For centuries, humans have viewed the universe as a vast, infinite expanse. The ancient Greeks envisioned the universe as a spherical, bounded system, with Earth at the center, surrounded by stars and planets. But with the advent of heliocentrism in the 16th century, which revealed that the Earth orbits the Sun, our understanding of the universe expanded drastically. As we learned more about the solar system and later about the galaxy and the universe at large, the idea of an infinite, ever-expanding cosmos became the accepted view. This perspective was further solidified in the 20th century with the discovery that the universe is expanding. Observations of distant galaxies showed that they are moving away from us, suggesting that the universe itself is stretching outwards, much like the surface of an inflating balloon. The concept of an expanding universe, coupled with the theory of cosmic inflation, which proposes that the universe underwent a rapid expansion shortly after the Big Bang, has been the foundation of modern cosmology. The idea of an infinite universe is comforting in its simplicity. If the universe is infinite, it means there is no boundary, no edge, just endless space that stretches on forever. But what if this traditional view is wrong? What if the universe is not infinite, but finite, contained within a massive cosmic bubble? Could the observable universe that we see, the cosmic horizon, be just the surface of a larger, more complex structure? The cosmic bubble. Concept: a closed system. The concept of a cosmic bubble presents a radically different view of the universe. Instead of envisioning an infinite cosmos, this theory proposes that our universe is contained within a bubble, a finite, self-contained system that exists within a much larger structure. This bubble, however, is not simply a localized patch of space, but could be part of a vast network of bubbles, each containing its own set of physical laws and properties. The bubble theory draws heavily on the idea of cosmic inflation, which suggests that the universe expanded at an exponential rate just after the Big Bang. According to this theory, our universe could be one of many bubbles created during this inflationary period. Each bubble could represent a distinct universe with its own set of physical constants and properties. The multiverse theory, which suggests that there are many universes, each with its own unique laws of physics, fits neatly within this framework. But unlike the traditional view of an infinite universe, the bubble model proposes that the universe we live in is a closed system. This means that there are physical boundaries to the universe, and what lies beyond those boundaries is unknown, perhaps even unknowable. The observable universe, the region of space we can detect and measure, is just one small part of a much larger cosmic structure. In this sense, our universe is akin to a giant soap bubble floating within a vast multidimensional space. The observable universe, a bubble within a larger reality. The concept of the observable universe is key to understanding the bubble theory. The observable universe refers to the portion of the universe that we can observe and measure using telescopes, satellites, and other instruments. This region is limited by the speed of light and the finite age of the universe. In other words, we can only observe the part of the universe that has had enough time for light to reach us since the Big Bang. The observable universe is not the entirety of the universe. It is just the portion of the cosmos that is within our reach. Beyond this cosmic horizon lies a vast, unknown expanse. According to the bubble theory, the observable universe is just one bubble of space-time within a larger, infinite structure. While we are confined to this bubble, other bubbles may exist, each representing its own universe with different physical properties and laws. These bubbles could be completely separated from each other, with no way to interact or influence one another. If our universe is truly a bubble within a larger reality, the implications are profound. First, it would mean that the universe is not as infinite as we once thought. Instead, it is confined within a closed system with boundaries that we cannot yet comprehend. This raises the question, what lies beyond the edge of our universe? Is there another bubble universe beyond ours, or are we the only bubble in existence? The role of inflation. How the cosmic bubble could have formed. To understand how the cosmic bubble theory fits into modern cosmology, we need to take a closer look at cosmic inflation. This theory, first proposed by physicist Alan Guth in the 1980s, suggests that the universe underwent an incredibly rapid expansion in the first fractions of a second after the Big Bang. During this brief period, the universe expanded exponentially, stretching from subatomic scales to vast sizes in an instant. Inflation explains several key features of the universe, such as its large-scale homogeneity and the distribution of galaxies. However, inflation also suggests that this rapid expansion did not stop with the creation of our universe. Instead, it continued indefinitely, creating an eternal inflation process that gives rise to bubble universes. Each bubble universe is a result of a localized region of space undergoing inflation, leading to the formation of a new, self-contained universe. These bubbles are completely separate from each other, with no way of communicating or interacting. The concept of eternal inflation fits seamlessly with the idea of a multiverse, where each bubble universe exists independently, governed by its own set of physical laws and constants. Some universes could be similar to ours, with similar laws of physics and the same fundamental forces. Others could be radically different, with entirely new laws governing matter, energy, and gravity. In this sense, our universe is just one bubble in a vast sea of other universes, each with its own unique properties. The connection to the multiverse. Infinite bubbles in infinite space. The idea of a cosmic bubble is closely tied to the multiverse theory, which posits that there are infinite universes, each with its own distinct properties and laws. The multiverse is not a new idea, but it has gained significant attention in recent years as scientists grapple with some of the deepest questions in cosmology and quantum mechanics. According to the multiverse theory, our universe is just one of an infinite number of universes that exist within a larger, infinite space. Each universe is a bubble that is formed through the process of cosmic inflation, and each one is governed by its own set of physical laws. These universes could vary in terms of their basic constants, such as the speed of light, the strength of gravity, and the nature of matter. In some universes, the conditions might be conducive to the development of life, while in others, life as we know it might not even be possible. The multiverse theory provides a potential solution to the fine-tuning problem, which asks why the physical constants of our universe are perfectly suited for life. In a multiverse, the fine-tuning might simply be a result of the vast number of possible universes, each with different properties. We happen to live in one of the universes where the conditions are just right for life to exist. In this way, the multiverse theory offers a possible explanation for the extraordinary balance of forces and constants in our own universe. The philosophical implications. Are we just one bubble among many? If we accept the possibility that we are living inside a giant cosmic bubble, it raises profound philosophical questions about the nature of reality, existence, and our place in the cosmos. If our universe is just one bubble in a much larger multiverse, what does that mean for the uniqueness of our universe? Are we simply a random outcome in a sea of infinite possibilities, or is there something inherently special about our bubble? The multiverse theory challenges the notion of a unique, purpose-driven universe, suggesting that everything we experience may be just one possible configuration in a much larger and more complex reality. This has profound implications for our understanding of existence, free will, and the nature of life itself. Are we truly special, or are we just one of an infinite number of possibilities? Conclusion: embracing the cosmic bubble. The idea that we could be living inside a giant cosmic bubble challenges everything we think we know about the universe. It forces us to reconsider our understanding of space, time, and the very nature of reality itself. If our universe is just one bubble in a vast multiverse, then the cosmos is far stranger and more complex than we ever imagined. As we continue to explore the universe and push the boundaries of our knowledge, we may one day uncover definitive evidence for the cosmic bubble theory. Whether or not this theory turns out to be correct, it offers a new perspective on the nature of the universe and our place within it. The universe is not as infinite as we once thought. It may be a bubble contained within a larger reality, and that is a truth worth exploring. The notion that we could be living inside a cosmic bubble is a radical departure from how we've traditionally understood the universe. For centuries, the prevailing view was that the universe is infinite, an endless expanse that stretches on forever in all directions. However, the idea that our universe might be a bubble within a much larger, potentially infinite structure is both perplexing and exhilarating. It challenges everything we thought we knew about space, time, and the fundamental nature of the cosmos. So, what exactly is the cosmic bubble theory? In essence, the theory proposes that our universe, everything from the Big Bang to the stars, planets, and galaxies, is contained within a vast bubble of space-time. This bubble is a self-contained, finite structure, and it could be part of a much larger multiverse, with other bubbles representing entirely different universes, each with its own unique physical laws and constants. Our observable universe, the one we can see, measure, and study, is just a small portion of a much larger, potentially infinite system of bubble universes. In this chapter, we will dive deep into the cosmic bubble theory, exploring its origins, how it fits within modern cosmology, and the implications it has for our understanding of space, time, and the nature of reality itself. We'll also examine how this theory interacts with other important cosmological concepts, such as cosmic inflation, the multiverse theory, and the observable universe. The origins of the cosmic bubble. The idea of the cosmic bubble is not entirely new. It has its roots in cosmic inflation, a theory that was proposed by physicist Alan Guth in the 1980s to explain the observed uniformity and large-scale structure of the universe. According to the theory of inflation, the universe underwent an incredibly rapid expansion in the first moments after the Big Bang. This expansion stretched space-time to enormous proportions, causing the universe to grow exponentially in size over a very short period of time. Inflation was proposed as a solution to several major problems in cosmology at the time, such as the flatness problem, why the universe appears to be so geometrically flat, and the horizon problem, why distant regions of the universe have the same temperature despite being separated by vast distances. Inflation provided a mechanism for the universe to become as homogeneous and isotropic as we observe it to be today. One of the key implications of cosmic inflation is that the universe we observe is only a small region of a much larger space. Inflation suggests that, during the early moments of the universe, space-time could have inflated not just in a single region, but across an infinite number of regions, each forming its own distinct universe. These regions of space-time could be thought of as bubbles, each one expanding and forming its own universe with its own physical laws and constants. The observable universe we live in could therefore be just one bubble in an infinite multiverse. The bubble universe concept and the multiverse theory. The idea of bubble universes is deeply tied to the multiverse theory, which proposes that there are many different universes, each with its own set of physical laws and constants. In the traditional view, our universe is the only one that exists, with its own unique properties and laws. But the multiverse theory challenges this view by suggesting that our universe is just one of many. In the context of the cosmic bubble theory, the multiverse can be visualized as a collection of individual bubbles floating within a much larger unobservable space. These bubbles represent entire universes, each with its own configuration of physical laws. Some of these universes might have properties similar to ours, while others might be completely different, where the constants of nature, such as the speed of light or the strength of gravity, are vastly different. In this framework, our universe is just one of many that exist in a cosmic sea, with no particular significance or central importance. The multiverse theory suggests that our universe, with all its complexities, is just one possible outcome of an infinite set of possibilities. It implies that there could be an infinite number of universes, each with different fundamental parameters. This opens up the tantalizing possibility that in another universe, life as we know it might not exist, or perhaps the laws of physics might be so different that the very concept of space and time is unrecognizable. Cosmic inflation and the creation of the bubbles. One of the central ideas behind the cosmic bubble theory is eternal inflation, the idea that the rapid expansion of space-time didn't stop after the formation of our universe, but continues to occur in some regions of space. According to the theory of eternal inflation, inflation doesn't just happen once, it happens repeatedly, creating a never-ending process of universe formation. Each time a region of space undergoes inflation, a new bubble universe forms. These bubble universes, once formed, become self-contained and independent from one another, each evolving according to its own set of physical laws. In this framework, the formation of a new universe is not a one-time event, but a continuous process. The Big Bang that we think of as the beginning of our universe could, in fact, be the birth of just one bubble within a much larger multiverse. The process of bubble formation could continue indefinitely, with new universes constantly emerging in a vast expanding cosmos. Eternal inflation also raises the possibility that the observable universe, the part of the universe that we can see and measure, is just a small fraction of a much larger structure. The observable universe is limited by the speed of light and the finite age of the universe, which means that we can only observe objects that are within a certain distance. However, beyond this horizon, there may be other universes, each with its own galaxies, stars, and physical laws. This idea challenges the notion that our universe is the only one that exists, and instead suggests that we live in a multiverse with countless other universes beyond our reach. The observable universe, a tiny piece of the puzzle. The observable universe is the part of the cosmos that we can see, detect, and study using telescopes and other instruments. It is defined by the distance that light can travel since the Big Bang, which is approximately 13.8 billion years. This means that the observable universe has a radius of about 46 billion light-years, and everything within this region is part of the universe we can study and understand. However, the observable universe is not the entire universe, it's just the portion that is within our reach. The theory of cosmic inflation suggests that there is much more beyond the observable universe, and that the universe we can see is just a small bubble within a larger, infinite cosmos. In fact, the observable universe may be just one slice of a much larger, ever-expanding structure of bubble universes. This concept of a larger, unobservable universe is supported by the idea of cosmic horizon, the point beyond which we cannot see or measure anything due to the limits of the speed of light and the age of the universe. While we can observe the light that has traveled to us from distant galaxies and stars, we cannot see beyond the cosmic horizon. What lies beyond that horizon could be an infinite number of other universes, each existing within its own bubble of space-time. How our universe could be a closed, self-contained bubble. The idea of our universe as a closed, self-contained bubble has profound implications for our understanding of space-time, the laws of physics, and the structure of the cosmos. In the traditional view, the universe is infinite and unbounded. Space stretches on forever, and there is no edge or limit. However, the cosmic bubble theory suggests that space itself could be finite and contained within a bubble, much like the surface of a soap bubble. If the universe is a bubble, it could have a boundary beyond which there is nothing. This boundary could represent the edge of the observable universe, where space-time behaves differently or becomes incomprehensible. The idea of a closed universe also raises the question of what lies beyond the bubble. Is the bubble we inhabit the only one in existence, or is it part of a larger structure, a multiverse of countless bubbles, each with its own unique properties? This idea challenges the conventional view of an infinite universe and suggests that there may be physical limits to space itself. If our universe is a bubble, it could be a finite structure with a beginning, an end, and a set of boundaries that we have yet to fully comprehend. These boundaries could hold the key to understanding the true nature of space and time and may provide new insights into the structure of the cosmos. What lies beyond the bubble? If our universe is indeed a bubble, one of the most intriguing questions is, what lies beyond it? The answer is uncertain, and the possibilities are endless. One possibility is that the universe is part of a vast multiverse with an infinite number of bubbles, each containing its own set of physical laws and constants. These bubbles could be entirely separate from one another, with no interaction or overlap, each existing in its own unique corner of the multiverse. Alternatively, the space beyond our bubble could be completely empty, an uninhabited, featureless void. In this view, our universe is isolated, and there is nothing beyond it. The nature of the space outside our bubble could remain an enduring mystery, one that we may never be able to explore or understand. Whether our universe is part of a multiverse or a solitary bubble in an empty void, the possibilities of what lies beyond the bubble challenge our fundamental assumptions about space, time, and the universe itself. As we continue to explore the cosmos and push the boundaries of our knowledge, we may one day discover the true nature of the bubble we inhabit and learn what lies beyond the horizon. Conclusion: a new perspective on the cosmos. The idea that we could be living inside a cosmic bubble forces us to rethink our entire understanding of the universe. It challenges the notion of an infinite, unbounded cosmos and suggests that space itself may have limits that we have yet to fully comprehend. The cosmic bubble theory fits seamlessly within the framework of cosmic inflation and the multiverse theory, offering a new perspective on the structure and origins of the universe. As we continue to explore the cosmos, we may find that the bubble theory offers a key to understanding some of the deepest mysteries of space and time. Whether or not we are truly living inside a giant cosmic bubble, the concept opens up new possibilities for understanding the universe and our place within it. The universe is far stranger and more complex than we ever imagined, and the discovery of new phenomena will continue to challenge our ideas and expand the boundaries of knowledge. The theory of cosmic inflation has become a cornerstone of modern cosmology, revolutionizing our understanding of the early universe and explaining some of the most perplexing aspects of the cosmos. However, when it comes to the concept of a cosmic bubble, inflation theory takes on a whole new meaning. Could space itself be a bubble, and if so, what does that mean for the universe we observe today? Cosmic inflation proposes that in the first fractions of a second after the Big Bang, the universe expanded at an astonishing rate, much faster than the speed of light. This rapid expansion smoothed out irregularities and set the stage for the formation of the universe we now observe. But what if inflation didn't stop with the formation of our universe? What if inflation continued on, creating not just our universe, but an infinite number of bubble universes, each one distinct and separate from the other? In this chapter, we will explore the role of inflation in the formation of cosmic bubbles. We will delve into the mechanics of inflation, how it could lead to the creation of bubble universes, and what this theory suggests about the nature of space-time itself. Is it possible that we are living inside a bubble, formed through an endless process of cosmic inflation? Could the universe we see, the stars, galaxies, and even the very fabric of space-time be just a small part of a much larger, more complex structure? The birth of inflation. Theory. To understand the cosmic bubble theory, we first need to revisit the origins of inflation. The theory was first proposed in the early 1980s by physicist Alan Guth, and it aimed to solve several critical problems in the standard Big Bang model. The traditional Big Bang theory suggested that the universe began from a singular point, an infinitely dense and hot state, but it had trouble explaining why the universe appears to be so uniform and smooth on large scales, or why distant regions of the universe have the same temperature despite being far apart. Guth's solution was that in the moments after the Big Bang, the universe went through a period of exponential expansion, a growth so fast that space itself expanded by an enormous factor in a fraction of a second. This period of inflation would have stretched the universe to such an extent that it erased any initial irregularities and set the stage for the formation of the uniform universe we observe today. One of the key predictions of inflation theory is that the universe should be flat, meaning that the geometry of spacetime is almost perfectly flat, and that the universe should be isotropic, meaning that it looks the same in all directions. These predictions were confirmed through observations of the cosmic microwave background radiation, CMB, which shows the faint afterglow of the Big Bang. The CMB is remarkably uniform, with only tiny fluctuations confirming the inflationary model. However, while inflation explains the smoothness of the universe, it also suggests something more profound. If inflation can occur once, it could potentially occur again, creating an eternal process of bubble formation that leads to an infinite multiverse of universes. This process could have given rise to an infinite number of bubble universes, each with different physical properties and laws. The mechanics of cosmic inflation and bubble universes. Cosmic inflation doesn't just explain the large-scale structure of the universe, it also provides a potential mechanism for the creation of bubble universes. According to the eternal inflation model, the universe's rapid expansion didn't cease after the creation of our observable universe. Instead, inflation continues in certain regions, producing new bubbles of space-time that each become their own distinct universe. To understand this concept, imagine the process of bubbling up in a boiling pot of water. As the water heats up, bubbles form and rise to the surface. Similarly, in the early moments of inflation, different regions of space could have inflated at different rates, creating bubbles of space-time. These bubbles could grow and develop into self-contained universes, each with its own set of physical laws and constants. Each bubble universe would be isolated from the others, existing in its own pocket of space-time. The fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, might differ from bubble to bubble, and each universe could follow its own trajectory, governed by its own set of physical rules. The idea of bubble universes emerging from eternal inflation aligns closely with the multiverse theory, which proposes that the universe we observe is just one of an infinite number of universes, each with its own properties. In this sense, our universe is not unique. It is just one bubble in a much larger sea of universes, each distinct and potentially governed by different physical laws. Is our universe a cosmic bubble? If inflation continues eternally, the universe we inhabit could simply be one bubble within an infinite collection of other universes. But is it possible that our universe, the one we see and experience, is itself a bubble in a larger structure? To explore this question, let's consider the characteristics of our observable universe. The observable universe is the region of space that we can detect and measure, and it is limited by the speed of light. Because light travels at a finite speed, we can only see objects whose light has had enough time to reach us since the Big Bang. This gives our observable universe a finite size, with a radius of about 46 billion light-years. Now, according to the cosmic bubble theory, the observable universe could be just one small bubble within a much larger cosmos. The edge of our observable universe would represent the boundary of our bubble, and beyond it lies another bubble, potentially filled with its own galaxies, stars, and physical laws. The implications of this idea are staggering. If we live in a bubble, then the universe we experience might be much smaller and more constrained than we once thought. The edge of our universe might not be the edge of reality. It could be just the boundary of one particular bubble in a vast multiverse. The observable universe, not the end, but a starting point. The observable universe is the region that defines what we can detect with current technologies, but this is not the full extent of the universe. In fact, it could be just the tip of the iceberg. What lies beyond the edge of our observable universe? In the bubble theory, beyond this boundary lies the unobservable universe, potentially an infinite number of other bubbles, each with its own unique set of physical laws. The expansion of the universe plays a critical role in defining the limits of what we can observe. As the universe continues to expand, distant galaxies move farther away, and the light from these galaxies is redshifted, making it more difficult for us to detect. Eventually, galaxies will move beyond the reach of our telescopes, and the light they emit will never be able to reach us. However, the concept of eternal inflation suggests that the universe itself continues to expand at an ever-increasing rate. The regions of space where inflation is still occurring are constantly creating new bubbles, each one expanding and forming its own universe. This means that the universe we observe could be just a tiny part of a much larger, ever-expanding multiverse. The cosmic horizon and the limitations of observation. The cosmic horizon represents the limits of our observable universe, the furthest point from which light has had time to travel since the Big Bang. The cosmic horizon is constantly moving outward as the universe expands, but it also represents a fundamental limit to what we can observe. Beyond the cosmic horizon lies a vast, unobservable region, and it is here that the theory of bubble universes comes into play. According to the bubble theory, the region beyond the cosmic horizon is not empty, but filled with other universes, each a bubble in its own right. These universes could be entirely separate from our own, with different physical constants, different laws of gravity, and perhaps even entirely different forms of matter and energy. In this sense, the cosmic horizon is not just a boundary. It is a doorway to an infinite number of other possibilities. But what happens when we try to understand what lies beyond the cosmic horizon? The reality is that we may never be able to observe what's beyond the limits of our universe. Even with the most advanced telescopes and technologies, the distances involved are so vast that we will never have direct access to the other bubbles of space-time. This raises the question, is the universe as we know it the only one that exists, or is it just a small part of a much larger reality? The end of inflation. What happens to the bubbles? The idea of eternal inflation raises another interesting possibility. What happens when inflation finally stops? If inflation continues forever, then new bubbles will keep forming, each creating its own universe. But at some point, inflation could cease in some regions and the bubbles would stop expanding. What would happen to these bubbles once inflation stops? Some theories suggest that when inflation ends, the energy from the inflationary process could be transferred into the creation of matter and radiation. This process could be similar to the Big Bang itself, where the energy released from inflation is transformed into particles, giving birth to galaxies, stars, and other cosmic structures. In this sense, the end of inflation could mark the birth of a new universe, one that begins as a bubble and expands outward, eventually becoming its own distinct, self-contained reality. Conclusion: the nature of space-time and the infinite cosmos. The theory of cosmic inflation and the creation of bubble universes challenges everything we thought we knew about the universe. If our universe is just one bubble in a larger, ever-expanding multiverse, it raises profound questions about the nature of space, time, and reality itself. Are we living in a finite bubble, or is the universe truly infinite? What lies beyond the edge of our observable universe, and how can we ever know what's out there? The answers to these questions are still unknown, but the pursuit of these answers is what drives the study of cosmology forward. As we continue to explore the universe, we may uncover new truths that reshape our understanding of the cosmos. Whether or not we live inside a cosmic bubble, the universe is far stranger and more complex than we can possibly imagine. And with each new discovery, we take one step closer to understanding the true nature of spacetime and the infinite cosmos that surrounds us. The idea that the universe might be a closed system is a thought-provoking and challenging concept, one that radically shifts how we perceive the nature of space, time, and reality itself. If the universe is truly a self-contained bubble, it would imply that there are limits, both physical and metaphysical, to the universe. A closed system, by definition, has boundaries, and the implications of those boundaries are profound, raising questions about the origin of the universe, what lies beyond the observable cosmos, and whether space itself is finite. In this chapter, we will explore the idea that our universe might be a closed system, a finite structure with a specific size, shape, and boundary. We'll delve into the nature of a closed system and how this idea fits within our current understanding of the universe. We'll also examine how modern cosmology, the laws of physics, and the discoveries of the past century challenge our notions of space as an infinite expanse. Could the universe have an edge, a boundary, or a limit to its expansion? Could space-time itself be finite, governed by hidden rules that we have yet to uncover? We will also discuss how the closed system model connects to some of the most fundamental concepts in modern physics, such as space-time curvature, the observable universe, cosmic inflation, and dark energy. By examining these ideas through the lens of a closed system, we can begin to understand how this theory fits into the broader framework of cosmology, and whether it can provide an alternative view to the traditional notion of an infinite, expanding universe. The concept of a closed system. A closed system in physics refers to a system that is isolated from its surroundings and does not exchange energy or matter with the external environment. This concept is most commonly applied to thermodynamics, where closed systems are studied to understand the flow of energy and matter. The idea of a closed system is usually contrasted with an open system, where energy and matter can flow in and out of the system, and an isolated system, which does not exchange energy, matter, or information with its surroundings. When applied to cosmology, the notion of a closed system suggests that the universe itself might be finite and self-contained, with boundaries or limits that define its size. The space-time in which we live would be a finite bubble within a larger structure, governed by physical laws that we have yet to fully comprehend. In this model, the universe would have an edge or boundary, beyond which there is nothing, or, more likely, there's an entirely different region of space-time that is inaccessible to us, perhaps governed by different physical laws or properties. The closed system theory is not without its challenges. The universe is currently expanding, and the idea of a finite closed system seems at odds with the expansionary model of the universe, which suggests that space itself is stretching over time, creating new regions of space that were once inaccessible. But what if the expansion of the universe doesn't mean an infinitely expanding cosmos, but rather the growth of a self-contained bubble? If this were true, the space-time fabric within the bubble would continue to stretch, but the universe as a whole would still be finite and limited by the bubble's boundary. Cosmic inflation. Expanding or contained? One of the most compelling pieces of evidence for the cosmic bubble theory comes from the theory of cosmic inflation, which suggests that the universe underwent an incredibly rapid expansion in the first moments after the Big Bang. This expansion, which lasted a fraction of a second, smoothed out any irregularities in the universe and set the stage for the large-scale structure we observe today. Inflation theory explains why the universe is so homogeneous and isotropic, the same in every direction, at large scales. It also accounts for the observed flatness of the universe, meaning that space-time is nearly perfectly flat on cosmological scales. But inflation also implies something else. The universe we observe could be just one bubble in an infinite sea of bubbles, each with its own distinct laws and physical properties. While inflation suggests that our universe grew from an almost infinitesimally small point to the vast cosmos we see today, it doesn't necessarily imply that the universe is infinite. Instead, it could mean that the universe is finite, but that its boundaries are not immediately apparent. If our universe is a bubble within an eternal inflationary process, it could be expanding continuously, but still be contained within a larger structure of other universes, each one separate, self-contained, and distinct. The idea of an infinite inflationary process does not necessarily contradict the idea of a closed system, but it does suggest that the bubble of space-time we inhabit could continue to grow indefinitely within its defined boundary. The universe might not be expanding into an infinite void, but rather into a larger, unobservable multiverse, with each bubble universe continuing to expand, evolve, and interact with its surroundings in ways we may not fully understand. The observable universe. Limits to our knowledge. One of the most important concepts in understanding whether the universe is a closed system is the idea of the observable universe. The observable universe is defined by the distance that light has been able to travel since the Big Bang, which occurred approximately 13.8 billion years ago. This means that the observable universe has a finite size, about 46 billion light-years in radius, and everything we can see, measure, and study falls within this region. However, the observable universe is not the entirety of the universe. It is simply the part of the cosmos that lies within our cosmic horizon, the limit imposed by the speed of light and the age of the universe. Beyond this horizon, there is more space, but it is beyond our reach. In the closed system model, the observable universe could be seen as the boundary of our cosmic bubble, and the space beyond it could be inaccessible to us, both physically and theoretically. The observable universe is also influenced by the expansion of space itself. As the universe expands, the light from distant galaxies is stretched or redshifted, making it more difficult to detect. Eventually, distant galaxies will move beyond the cosmic horizon, and their light will no longer be able to reach us. This raises the question, is the observable universe just a small bubble in a larger infinite cosmos, or is it the entirety of space and time? The edge of the universe. What lies beyond? The concept of a boundary to the universe is one of the most profound and controversial ideas in modern cosmology. If the universe is a closed system, then there must be some sort of edge or limit to the space-time fabric we inhabit. But what lies beyond this edge? In the traditional view of an infinite universe, there is no edge. Space stretches out infinitely in all directions, and there is no boundary beyond which the universe ends. However, the closed system model suggests that there is a limit to the universe, and beyond this limit lies a region of space that we cannot access. This space could be completely different from our own, governed by different laws of physics, or it could be empty, without any structure or matter at all. Some theories suggest that the edge of the universe might be a cosmic boundary, a physical limit beyond which space-time no longer behaves as we understand it. In this view, the universe we observe is just one bubble within a larger infinite multiverse, and each bubble is isolated from the others. The edge of the universe might mark the transition from our bubble to the next, where space-time behaves differently, or where different physical laws govern the behavior of matter and energy. Alternatively, Some scientists speculate that there is no edge at all, just an infinite continuum of space and time. In this view, the universe is not a closed system, but rather an open, infinite structure that continues to expand and evolve. But if this is the case, then the question remains, what drives this expansion? And how does space-time behave at the limits of the universe? Dark energy, the mysterious force. The edge of the universe. One of the most significant discoveries in cosmology in the past few decades has been the observation that the expansion of the universe is accelerating, not slowing down as once expected. This accelerated expansion is thought to be caused by a mysterious force known as dark energy, a form of energy that permeates space and causes it to expand at an increasing rate. Dark energy accounts for roughly 68% of the total energy content of the universe, but little is known about its true nature. Some theories suggest that dark energy is a property of space itself, while others propose that it could be a manifestation of a deeper, more fundamental force in the universe. If our universe is a closed system, dark energy could play a critical role in the expansion of the bubble. The accelerating expansion could mean that our universe is stretching out toward the boundaries of its bubble, and dark energy could be the force that drives this expansion. If the bubble theory is correct, dark energy could be the key to understanding how space-time behaves on the largest scales and could hold the answer to the ultimate fate of the universe. The role of gravity. Curvature of space-time. One of the defining features of general relativity is the curvature of space-time. According to Einstein's theory, massive objects like stars and planets curve the fabric of space-time around them, creating the phenomenon we perceive as gravity. This curvature is not just limited to objects with mass. Space-time itself is curved, and the curvature of space-time governs the motion of everything in the universe. In the closed system model, the curvature of space-time could play a critical role in defining the boundaries of the universe. If the universe is a bubble, the curvature of space-time could create a kind of bubble shape, a finite closed surface with edges beyond which space-time behaves differently. This would explain the observed expansion of the universe as the space-time fabric of our bubble stretches and warps over time. Gravity, in this context, would not just be a force between objects with mass, it would also be the force that governs the structure of the entire universe. The curvature of space-time could provide the key to understanding the limits of the universe, the behavior of galaxies, and the fate of the cosmos. Conclusion. A new view of the universe. The idea that we live in a closed system forces us to rethink our understanding of the universe. No longer is the universe an infinite expanse stretching out forever. Our universe could be a finite, self-contained bubble. This bubble, formed through the process of cosmic inflation, is expanding and evolving, but it is still bounded by limits that we have yet to fully understand. As we continue to explore the cosmos, the idea of a closed universe could provide a framework for understanding the ultimate fate of the cosmos. Could the universe eventually stop expanding, collapse in on itself, or continue to stretch indefinitely? The answers to these questions will depend on our understanding of the forces that shape the universe, from dark energy to gravity to the curvature of space-time. The closed system model challenges the traditional view of an infinite universe, offering a new perspective on the structure of space-time. As we look beyond the cosmic horizon, we may one day uncover the true nature of the universe and its boundaries, offering a glimpse into the deeper mysteries of the cosmos. The cosmic microwave background radiation, CMB, is one of the most profound and important discoveries in modern cosmology. It represents the faint afterglow of the Big Bang, the very first light emitted when the universe was just 380,000 years old. This radiation, which permeates the entire universe, offers crucial insights into the early stages of the cosmos, its age, and its structure. But when we consider the possibility that we live inside a cosmic bubble, the CMB takes on even greater significance. Could anomalies in the CMB provide evidence that our universe is indeed a self-contained bubble, floating within a larger multiverse? In this chapter, we will explore how the CMB supports or challenges the idea of the cosmic bubble theory. We'll dive into the nature of the CMB, its origins, and the key patterns that it reveals. We'll also examine how these patterns may hint at the boundaries of our universe, the existence of other universes, or even the potential of our universe being a bubble in a much larger and infinite multiverse. The CMB holds a wealth of information, and in the context of the bubble theory, it could provide the key to unlocking some of the greatest mysteries of the universe. What is the cosmic microwave background radiation? The cosmic microwave background radiation is often described as the afterglow of the Big Bang. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, allowing light to travel freely through space for the first time. This moment, known as the recombination epoch, marked the end of the photon decoupling phase, where the universe went from being opaque to transparent. The light that was emitted at this time has been traveling ever since, and it forms the CMB, which we can detect today. The CMB is a faint uniform radiation that fills the universe, and it is composed of microwaves, long wavelength radiation that has been stretched as the universe expanded. The temperature of the CMB is about 2.7 Kelvin, just above absolute zero, and it is one of the most important pieces of evidence supporting the Big Bang theory. The radiation itself is almost perfectly uniform, with only tiny fluctuations, or anisotropies, which provide a wealth of information about the early universe's structure and composition. By studying the CMB, cosmologists can learn about the universe's early history, including the distribution of matter and energy, the rate of expansion, and even the geometry of the cosmos. In essence, the CMB acts as a snapshot of the universe's infancy, frozen in time, and it holds critical clues to understanding both the large-scale structure of the universe and its origins. The anomalies in the CMB, clues to a cosmic bubble. One of the most intriguing aspects of the CMB is the presence of anisotropies, slight temperature variations that are visible when the CMB is mapped across the sky. These fluctuations, while extremely small, about 1 part in 100,000, are significant because they provide a glimpse into the distribution of matter and energy in the early universe. These fluctuations are the result of sound waves that propagated through the hot, dense plasma that filled the early universe. These temperature variations are not random. They follow patterns that can be traced back to the initial conditions of the universe. The angular power spectrum of the CMB maps the different sizes of these fluctuations across the sky, and it offers a detailed view of the universe's geometry and composition. The CMB has provided definitive evidence for dark matter and dark energy, two mysterious components that account for the vast majority of the universe's mass-energy content. But beyond these well-understood features, there are some anomalies in the CMB that have puzzled cosmologists and physicists. These anomalies are subtle, but they may hold the key to understanding the true nature of our universe. Among the most noteworthy anomalies are the cold spot and the axis of evil, both of which suggest the possibility that our universe is not just a single isolated entity, but may be part of a larger, more complex system, a multiverse of bubble universes. The cold spot, a possible window into the multiverse. One of the most intriguing features of the CMB is the cold spot, a large, unexplained region in the sky that is colder than the surrounding areas by about 100 microkelvins. This cold spot, which was first discovered in 2004, is a profound mystery because it does not fit the standard model of cosmic inflation. In the inflationary model, the universe expanded rapidly and evenly, and there should be no large regions that deviate significantly from the average temperature. So what could explain this anomaly? One possibility is that the cold spot is a collision with another bubble universe. According to the multiverse theory, if our universe is part of a larger structure of universes, then it's possible that the cold spot could be the result of our bubble colliding with another bubble. The interaction between two expanding bubbles could cause ripples or fluctuations in the fabric of space-time, which might manifest as a cold spot in the CMB. This idea is supported by the concept of eternal inflation. As we discussed in earlier chapters, the process of eternal inflation suggests that new universes are constantly being created, each one expanding rapidly and independently from the others. If our bubble universe collided with another during its formation, the resulting disturbance in space-time could leave a detectable mark in the CMB. The cold spot could, therefore, be a relic of this cosmic collision, offering a tantalizing clue that our universe is part of a larger multiverse of bubble universes. The axis of evil. A mysterious alignment. Another anomaly in the CMB is the axis of evil, a strange alignment of temperature fluctuations in the CMB that runs along a particular axis. This alignment, which was first noticed in 2005, is odd because, according to the laws of physics, temperature fluctuations in the CMB should be random and isotropic, with no preferred direction. However, the axis of evil suggests that there is some sort of large-scale alignment in the CMB which defies expectations. Some cosmologists have speculated that this alignment might be due to the influence of an external factor, such as the presence of a nearby universe or the effects of cosmic strings, theoretical one-dimensional objects that could stretch across space-time. However, another possibility is that the axis of evil could be evidence of a larger structure, a multiverse of bubble universes where the directionality of the CMB fluctuations could be influenced by the geometry of the space between universes. The alignment might represent a residual effect from the interaction between our universe and other universes in the multiverse. The axis of evil remains one of the most puzzling anomalies in the CMB, and while its true cause is still unknown, it opens up the possibility that our universe is not the isolated system we once thought. Instead, it may be part of a much larger, interconnected web of universes, each one interacting with the others in ways we have yet to fully understand. What do these anomalies mean for the cosmic bubble theory? The cold spot and the axis of evil provide intriguing evidence that our universe may not be an isolated, independent entity, but rather part of a much larger, more complex system. If these anomalies are the result of interactions between bubble universes, they could be the first tangible evidence of the multiverse, a theory that proposes that our universe is just one bubble in an infinite, ever-expanding collection of universes. The cosmic bubble theory suggests that the universe we observe is just one bubble in a larger, infinite sea of universes, each with its own distinct properties and physical laws. The CMB anomalies, particularly the cold spot, may provide a glimpse into the true nature of the universe, revealing that the space-time we inhabit is not the end-all, be-all of existence. Instead, it may be one small pocket of reality, floating in a vast multiverse with other universes surrounding us, each with its own laws and properties. If the CMB anomalies are indeed the result of interactions between universes, they could hold the key to understanding the true nature of the multiverse. By studying these anomalies in greater detail, we could gain insight into the boundaries of our universe, the nature of dark energy, and the possibility of other universes beyond our reach. The CMB may be offering us a glimpse into a much larger, more complex reality, one that challenges everything we thought we knew about space, time, and the cosmos. The future of CMB research and cosmic bubble theory. As technology improves, we will be able to study the cosmic microwave background with greater precision. The launch of advanced space telescopes such as the James Webb Space Telescope and the Planck satellite is expected to provide more detailed maps of the CMB and allow scientists to look for further anomalies that might support the cosmic bubble theory. By continuing to explore the CMB and its anomalies, we may be able to confirm or refute the idea that we are living in a bubble universe. If the cold spot and the axis of evil are indeed the result of bubble collisions or interactions with other universes, they could represent some of the most groundbreaking discoveries in cosmology. The study of the CMB is just one part of the ongoing exploration of the universe and its mysteries. As we push forward in our understanding of space-time, dark energy, and the multiverse, the CMB will continue to play a critical role in unraveling the deepest secrets of the cosmos. Conclusion. The CMB is a window into the multiverse. The cosmic microwave background radiation is a key piece of evidence that provides insight into the early universe. But when viewed through the lens of the cosmic bubble theory, the CMB becomes something much more, potential evidence that our universe is not an isolated independent system, but one bubble in an infinite multiverse. The cold spot and the axis of evil are just the beginning of what could be a major breakthrough in our understanding of the universe's true structure. As we continue to study the CMB and uncover new anomalies, we may discover that our universe is part of a much larger, interconnected system of universes, each with its own unique laws of physics and properties. The possibility of a cosmic bubble is not just a fascinating idea. It could be the key to understanding the true nature of the universe and the reality that surrounds us. The concept of the multiverse is one of the most revolutionary ideas in modern physics, offering a radically different perspective on the nature of reality. Instead of viewing our universe as the only one that exists, the multiverse theory suggests that there are countless other universes, each with its own distinct properties, physical laws, and possibly even different dimensions of space and time. This theory challenges everything we thought we knew about the cosmos, and it is intimately connected to the concept of cosmic bubbles. If our universe is indeed one of many bubbles in a larger multiverse, it implies that the reality we experience is just one of infinite possibilities. Each bubble, or universe, could have different conditions and laws, and some of these universes might be vastly different from our own, while others might bear a striking resemblance to ours. The multiverse could be far stranger and more diverse than we can even imagine. In this chapter, we will explore the relationship between the cosmic bubble theory and the multiverse concept. We will examine the various types of multiverses that have been proposed in modern cosmology, how bubble universes fit into these models, and what implications this theory has for our understanding of reality, space, and time. Could we really be living inside a bubble, part of an infinite, eternally expanding collection of universes? And if so, what does that mean for our place in the cosmos? The many faces of the multiverse theory. The multiverse theory is not a single unified idea, but a collection of different theories that all suggest the existence of multiple universes. While the idea of many universes has been explored for centuries in philosophy and science fiction, it wasn't until the 20th century that serious scientific theories began to take shape. Today, there are several different multiverse models, each with its own implications for the nature of space and reality. The idea that we could be living in a multiverse of bubble universes is closely tied to the theory of eternal inflation, which proposes that the universe is constantly undergoing an inflationary phase, creating new bubbles of space-time that become self-contained universes. Each of these bubbles would form independently of the others, with its own set of physical laws, constants, and properties. Some of the most prominent models of the multiverse include Level 1, Level 2, Level 3, and Level 4 multiverses, each suggesting different ways that universes might exist and interact. Level 1, Multiverse, infinite space, infinite possibilities. The Level I multiverse is the simplest and most intuitive version of the multiverse theory. It proposes that the universe is infinite, and as a result, it contains all possible configurations of matter and energy. In this model, the universe is so vast that, given infinite space and time, the arrangement of particles and energy will inevitably repeat itself. Therefore, there must be regions of space that are identical to ours, with exact copies of planets, stars, and even life forms. The Level 1 multiverse doesn't require the existence of other universes as separate entities. Rather, it suggests that our universe itself is infinite and that identical regions of space exist somewhere far beyond our observable horizon. If we wait long enough, we will eventually encounter regions of space that are identical to our own, with planets, stars, and possibly even versions of ourselves. This concept relies on the idea that space is infinite and that, with infinite time, all possibilities will eventually occur. Level 2. Multiverse, bubble universes with different laws of physics. Level 2. Multiverse is a more complex and fascinating concept, suggesting that our universe is just one of many bubbles created by eternal inflation. In this model, each bubble is a separate universe with its own set of physical laws and constants. The process of eternal inflation means that new universes are constantly being created, each one forming from an inflating region of spacetime. Each of these bubble universes could have vastly different properties. For example, one universe could have different laws of gravity, while another might have different fundamental particles or forces. The physical constants, such as the speed of light or the strength of the electromagnetic force, could vary from bubble to bubble. This model of the multiverse proposes that the universe we live in is just one bubble among many, each with its own distinct characteristics. Some bubbles might have similar conditions to ours, while others could be so different that life as we know it would be impossible. The Level 2 multiverse connects directly to the cosmic bubble theory, as it suggests that our universe is itself one of many bubbles in a vast, expanding multiverse. These bubbles form independently, each one governed by its own set of rules, and they may never interact with each other. The idea of bubble universes challenges our traditional notions of space-time and raises profound questions about the limits of our reality. Level 3. Multiverse, the many worlds. Interpretation of quantum mechanics. The Level 3 multiverse arises from the many worlds interpretation of quantum mechanics. In quantum mechanics, particles don't have definite states until they are measured or observed. Instead, they exist in a superposition of multiple states, and it is only when we observe them that they collapse into a single state. According to the many worlds interpretation, every time a quantum measurement is made, the universe splits into multiple branches, with each possible outcome occurring in a separate universe. In this view, there's a vast number of parallel universes, each corresponding to a different possible outcome of every quantum event. For example, if you flip a coin, the many worlds interpretation suggests that there are two separate universes, one where the coin lands heads up and one where it lands tails up. This model suggests that all possibilities, no matter how small, happen simultaneously in separate universes, leading to an infinite number of parallel worlds. The Level 3 multiverse is more philosophical and speculative than the Level 2 model, as it relies on the counterintuitive principles of quantum mechanics. However, it raises fascinating questions about the nature of reality. If every possible outcome of every event occurs in a parallel universe, then the multiverse becomes an infinite array of versions of ourselves, living out all possible lives in parallel timelines. This interpretation of quantum mechanics is controversial, but it remains one of the most thought-provoking models of the multiverse. Level 4. Multiverse, universes with different mathematical structures. The Level 4 multiverse takes the idea of parallel universes to an extreme. Proposed by theoretical physicist Max Tegmark, the Level 4 multiverse suggests that there are universes with completely different mathematical structures from our own. Instead of just different physical laws, the universes in a Level 4 multiverse could have entirely different sets of rules for how the universe operates at the most fundamental level. In this model, the multiverse is not just a collection of different universes with varying laws of physics, but a collection of universes with entirely different mathematical frameworks. Each universe would be governed by a different set of principles, and the very nature of reality could be vastly different from what we experience. Some of these universes could be so different that they are beyond our comprehension, existing in dimensions of space and time that we cannot even imagine. The Level 4 multiverse challenges our understanding of reality at a fundamental level, suggesting that the laws of physics we know might not be universal, but rather just one set of rules among many. This radical idea forces us to rethink everything we know about the cosmos and the nature of existence itself. The cosmic bubble and the multiverse, connecting the dots. So how does the idea of cosmic bubbles connect to the multiverse theory? At its core, the concept of the cosmic bubble is simply one possible manifestation of the multiverse. If the universe is formed through the process of eternal inflation, then it is part of a larger infinite structure of bubbles, each one representing a separate universe with its own set of properties and physical laws. The cosmic bubble theory aligns most closely with the Level 2 multiverse, where each bubble universe is created through inflation and exists independently of the others. However, the other multiverse levels, Level 1, Level 3, and Level 4, are also interconnected with the idea of cosmic bubbles, as they all propose the existence of multiple universes, each with its own distinct characteristics. Whether these universes are separated by space and time, quantum events, or entirely different mathematical frameworks, they all challenge the idea that our universe is the only one that exists. In this view, our universe could be just one bubble in an ever-expanding sea of universes. The concept of a cosmic bubble fits neatly into the multiverse theory, suggesting that the universe we observe is not the end-all, be-all of existence, but one small part of a vast, infinite cosmos. The implications of this idea are profound, as it challenges everything we know about the universe and raises new questions about the nature of space, time, and reality. The role of dark matter and dark energy in the multiverse. The discovery of dark matter and dark energy has reshaped our understanding of the universe. Together, these mysterious components make up about 95% of the universe's mass energy content, but we still don't fully understand what they are or how they work. Could dark matter and dark energy be related to the cosmic bubble theory and the multiverse? One possibility is that dark energy could be the force that drives the expansion of the multiverse. If each bubble universe is expanding at an accelerating rate, dark energy could be responsible for the continued growth of each bubble. This mysterious force might also play a role in determining the size and properties of each universe within the multiverse. Similarly, dark matter could be the key to understanding the gravitational effects between bubbles and how they interact with one another. The study of dark matter and dark energy could provide critical insights into the nature of the multiverse. By understanding these forces, we may be able to unlock the secrets of the cosmic bubbles and gain a deeper understanding of the true structure of the universe. Conclusion: the infinite possibilities of the multiverse. The multiverse theory and the idea of cosmic bubbles offer a radically different perspective on the nature of the universe. Instead of a single, isolated cosmos, we could be living in an infinite sea of universes, each one distinct, with its own set of laws and properties. The concept of a multiverse challenges everything we think we know about space, time, and reality, and it opens up a universe of possibilities that we are only beginning to explore. As we continue to study the cosmos, the multiverse theory will play an increasingly important role in shaping our understanding of the universe. Whether through the study of the cosmic microwave background radiation, the discovery of new dark matter or dark energy, or the development of new theoretical models, the idea of multiple universes will continue to drive scientific inquiry and exploration. In the end, the multiverse theory offers a humbling realization. The universe we see, the universe we inhabit, may be just one bubble in a vast, infinite, and ever-expanding cosmos. The possibilities are truly infinite. The universe as we know it is composed of much more than just ordinary matter. While we can see stars, planets, and galaxies through telescopes, there is a hidden aspect of the universe that has eluded direct observation. This invisible component is made up of dark matter and dark energy, two mysterious forces that make up approximately 95% of the universe's mass energy content. Together, they govern the dynamics of galaxies, the expansion of the universe, and possibly even the structure of the multiverse itself. In this chapter, we will explore the nature of dark matter and dark energy and examine how they might relate to the cosmic bubble theory. Could these hidden forces play a crucial role in the formation and expansion of cosmic bubbles? And if we live inside a bubble universe, how might dark matter and dark energy influence the boundaries and properties of our bubble? Understanding these forces is key to unlocking the deeper mysteries of the cosmos and could provide critical insights into the true nature of space-time. What is dark matter? Dark matter is one of the most elusive components of the universe. It doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet, despite its invisibility, Scientists have inferred its existence based on its gravitational effects on visible matter. Dark matter accounts for about 27% of the universe's total mass energy content, yet we have no direct way of detecting or observing it. The presence of dark matter was first suggested by astronomers in the 1930s, when Fritz Zwicky observed that galaxies and galaxy clusters were moving too quickly to be held together by the visible matter alone. If the universe were made up only of the visible matter we can see, stars, gas, and dust, then galaxies in these clusters would be flying apart due to insufficient gravitational pull. The fact that galaxies stay bound together suggested that there must be something else, something invisible, providing additional gravitational force. This unseen substance was later dubbed dark matter. Further evidence for dark matter came in the 1970s when Vera Rubin observed the rotation curves of galaxies. The stars in the outer regions of galaxies were moving faster than expected, based on the amount of visible matter present. According to Newtonian mechanics, stars farther from the galactic center should move more slowly, as they are further from the galaxy's gravitational core. However, Rubin's data showed that stars in the outer regions of galaxies were rotating at much higher speeds than expected, implying the presence of additional mass that could explain the gravitational pull. Dark matter does not interact with electromagnetic radiation, light, X-rays, radio waves, meaning it is invisible to telescopes. However, it does interact with regular matter through gravity, and this is how we detect its presence. The exact nature of dark matter remains a mystery, but scientists have proposed several potential candidates, such as weakly interacting massive particles, WIMPs, and axions, which are theoretical particles that might explain the gravitational effects we observe. What is dark energy? Dark energy is an even more mysterious force than dark matter. While dark matter is thought to exert a gravitational pull, dark energy is believed to work in the opposite way, driving the accelerating expansion of the universe. Dark energy accounts for about 68% of the total mass energy content of the universe, making it the largest and most enigmatic component of the cosmos. The existence of dark energy was first suggested in 1998 when two independent teams of astronomers observed the redshift of distant supernovae. These supernovae appeared dimmer than expected, which meant they were farther away than previously thought. This discovery led to the realization that the expansion of the universe is not slowing down, as had been assumed, but instead accelerating. The force responsible for this accelerated expansion was dubbed dark energy. Dark energy is thought to be a cosmological constant, a constant energy density that fills space homogeneously. It exerts a repulsive force that counteracts the attractive force of gravity, causing galaxies to move apart at an ever-increasing rate. While we do not fully understand the nature of dark energy, it is believed to be a fundamental aspect of the universe's structure, influencing the evolution and fate of the cosmos. The role of dark matter and dark energy in the cosmic bubble. In the context of the cosmic bubble theory, dark matter and dark energy take on even more importance. The idea that our universe is a self-contained bubble within a larger, infinite multiverse suggests that the dynamics of space-time within the bubble are influenced by these hidden forces. But how exactly do dark matter and dark energy contribute to the formation, structure, and expansion of cosmic bubbles? Dark matter's role in the bubble structure. Dark matter's influence on the structure of galaxies and galaxy clusters is well established. It provides the gravitational pull that keeps galaxies together and governs the motion of galaxies within clusters. But could dark matter also play a role in the formation of bubble universes? In the cosmic bubble model, dark matter could contribute to the density and structure of individual bubbles. If each bubble universe forms through the process of cosmic inflation, dark matter could help shape the structure of the universe within the bubble, affecting the distribution of galaxies, stars, and other cosmic objects. The presence of dark matter would also influence the growth of the bubble, acting as a source of gravitational pull that helps keep the bubble together as it expands. Moreover, if our universe is part of a larger multiverse, dark matter might be one of the forces that differentiates one bubble from another. Each bubble universe could have its own unique distribution of dark matter, which could affect the properties of space-time and the laws of physics within that bubble. For example, the density of dark matter in a given bubble might influence the formation of galaxies, stars, and black holes, creating vastly different structures in different universes. Dark energy and the expansion of the bubble. Dark energy plays a critical role in the accelerated expansion of the universe, and it may also influence the expansion of cosmic bubbles. In the eternal inflation model, new bubbles of space-time form continually, each one expanding and evolving independently. The expansion of these bubbles could be driven by a form of dark energy that exists within each bubble. In this scenario, dark energy could act as a kind of engine that drives the growth of each bubble universe, causing it to expand at an increasing rate. Just as dark energy accelerates the expansion of our observable universe, it might have a similar effect on the bubble itself, pushing its boundaries outward. This expansion could continue indefinitely, as long as the dark energy remains constant within the bubble. The presence of dark energy could also affect the boundaries of the bubble universe. If dark energy is responsible for the accelerated expansion of the bubble, it might create a situation where the bubble grows faster than the speed of light, pushing the universe's edges beyond our observable horizon. This raises the question of whether there are any physical limits to the expansion of the bubble, or if it could continue expanding indefinitely, potentially leading to the creation of new bubbles in a never-ending cycle of cosmic inflation. Dark matter and dark energy. A connection between bubbles? While dark matter and dark energy seem to have very different effects on the universe, there could be an underlying connection between the two. Some theories suggest that dark matter and dark energy could be manifestations of a deeper, more fundamental force that governs the behavior of space-time itself. This force might act differently in each bubble universe, leading to variations in the density of dark matter and the strength of dark energy across the multiverse. In this view, dark matter and dark energy could be intimately connected, and their effects on the expansion and structure of the bubble universes could provide critical insights into the nature of the multiverse. If dark matter and dark energy are the result of a more fundamental force, understanding how they interact could reveal the underlying principles that govern the behavior of space-time within and between bubbles. The fate of the cosmic bubble. Dark energy's role in the end of the universe. The role of dark energy in the expansion of the universe raises profound questions about the ultimate fate of our universe. In the current cosmological model, dark energy is driving the accelerated expansion of the universe, and if this expansion continues indefinitely, it could lead to the heat death of the universe, a state in which all matter is spread thinly across an ever-expanding void, with no possibility for further life or structure. If the universe is indeed a bubble within a larger multiverse, dark energy could play a similar role in the ultimate fate of the bubble itself. The constant expansion driven by dark energy could continue indefinitely, stretching the space-time of the bubble until it reaches a state of maximum entropy. This scenario raises the question of whether the bubble universe will eventually reach a breaking point, where the continued expansion leads to the collapse of space-time itself, or if it will simply continue expanding forever. Alternatively, some theories suggest that the influence of dark energy could eventually change, causing the expansion of the bubble to slow down or reverse. If dark energy's properties change over time, it could lead to the collapse of the bubble, an event sometimes referred to as the Big Crunch. This scenario would mark the end of the bubble universe, but it could also give rise to a new cycle of cosmic inflation with a new bubble forming in its place. Conclusion. Dark matter and dark energy in the cosmic bubble. Dark matter and dark energy are two of the most enigmatic components of the universe. While dark matter is responsible for the gravitational structure of galaxies and clusters, dark energy drives the accelerated expansion of space itself. In the context of the cosmic bubble theory, both forces play a crucial role in shaping the structure, growth, and fate of the bubble universes. As we continue to study these forces, we may unlock new insights into the true nature of the multiverse and the fundamental forces that govern space-time. If our universe is indeed a bubble in a larger, infinite multiverse, dark matter and dark energy could provide the key to understanding how these bubbles form, evolve, and ultimately meet their end. The exploration of dark matter and dark energy is far from over, and as we develop more advanced technologies and theoretical models, we may uncover new discoveries that challenge everything we think we know about the universe. The cosmic bubble theory offers a fresh perspective on the universe, and dark matter and dark energy could be the keys to unlocking the deeper mysteries of the cosmos. The notion that we could be living inside a simulation, a simulated universe, has been a topic of philosophical speculation for centuries. However, in the 21st century, the idea has moved from philosophy into the realm of serious scientific inquiry. The simulation hypothesis proposes that the reality we perceive with its stars, galaxies, and the fabric of space-time itself might not be real at all, but instead a sophisticated computer simulation created by a far more advanced civilization. This mind-bending theory challenges everything we think we know about existence and raises profound questions about the nature of reality, consciousness, and our place in the universe. In this chapter, we will explore the simulation hypothesis and its connection to the concept of the cosmic bubble theory. Could our universe, with its seemingly infinite space and time, be nothing more than a digital construct, a highly advanced program running on the hardware of an artificial intelligence or some kind of hyper-powerful supercomputer? How does this theory fit within the framework of modern cosmology and the idea of multiple bubble universes? And if we are living inside a simulation, what does that mean for our understanding of space-time, physics, and the multiverse? We will delve into the philosophical and scientific foundations of the simulation hypothesis, examining the arguments for and against it, and exploring its implications. For the nature of the multiverse, could it be that we are not inside a natural universe, but inside a digital simulation running in a larger external reality that we can't perceive? If so, how does this idea challenge our notions of the universe, our consciousness, and even the multiverse itself? The simulation hypothesis. What is it? The simulation hypothesis suggests that the universe we experience might not be real in the traditional sense, but rather a simulation created by an advanced civilization or superintelligence. According to this theory, everything we perceive, our thoughts, experiences, the stars, planets, and galaxies, could be the product of an artificial program running on a much more advanced computational system. The most well-known proponent of this idea is the philosopher Nick Bostrom, who argued in 2003 that there are three possibilities for the future of intelligent civilizations. 1. The probability of civilizations reaching a level of technology capable of running realistic, large-scale simulations of the universe is very low, meaning that it is unlikely that advanced civilizations will ever have the capability or the desire to create such simulations. 2. Advanced civilizations are technologically capable of running such simulations, but they do not do so, perhaps because they have ethical or philosophical concerns, or because they have moved beyond the need for simulation-based experimentation. 3. We are almost certainly living in a simulation, since advanced civilizations may create many simulations of their past, and the number of simulated realities would vastly outnumber the number of real realities, meaning that the odds are that we are living in one of these simulated universes. Bostrom's argument is based on the assumption that a sufficiently advanced civilization would have the computational power to simulate a universe so complex that its inhabitants, us for example, would never be able to detect that they were living in a simulation. In this scenario, the real universe exists outside of the simulation, and the reality we experience is nothing more than a digital construct. While Bostrom's argument is philosophical in nature, it has inspired a wide range of discussions and debates in both philosophy and science, with some physicists and cosmologists seriously considering the possibility that we could be living inside a simulation. Theoretical support for the simulation hypothesis. The simulation hypothesis is not purely speculative. In fact, There are several scientific and philosophical ideas that provide indirect support for the theory. Some of these ideas come from the realm of quantum mechanics, information theory, and cosmology, offering intriguing possibilities that align with the idea of a simulated universe. The nature of quantum mechanics and digital reality. One of the most compelling aspects of the simulation hypothesis comes from the field of quantum mechanics, the branch of physics that deals with the behavior of particles on the smallest scales. Quantum mechanics has revealed that the universe is fundamentally discrete, not continuous, at its most basic level. Particles don't have definite positions until they are measured, and they can exist in multiple states simultaneously, a phenomenon known as superposition. These strange, counterintuitive behaviors suggest that the fundamental fabric of the universe might not be continuous, but instead made up of quantized units of spacetime, like pixels on a screen. This discrete nature of the universe is similar to how a computer simulation works. Just as pixels on a digital screen combine to form an image, quantum bits of information could combine to form the reality we perceive. This analogy has led some physicists, like David Deutsch, to suggest that the laws of quantum mechanics may point to the possibility of a universe that is fundamentally digital in nature, just like a simulation. According to this view, the universe could be programmed in a way that mimics the behaviors we observe in nature. The holographic principle, reality as a projection. Another important concept that connects the simulation hypothesis to the idea of a cosmic bubble is the holographic principle. The holographic principle suggests that the entire universe could be a projection of information stored on a two-dimensional surface at the edge of space-time. This idea arose from studies of black holes and the nature of entropy, particularly in relation to black hole thermodynamics. According to the holographic principle, the three-dimensional universe we experience might be a projection of a two-dimensional surface, much like how a hologram is a three-dimensional image encoded onto a two-dimensional surface. This principle has gained significant traction in theoretical physics, especially in relation to quantum gravity and the study of the AD-CFT correspondence, a type of duality in string theory. The holographic principle suggests that space-time and even the laws of physics could be an illusion, an elaborate program running on a computational substrate. If the universe is indeed a holographic projection, it could be interpreted as a simulation created from a much deeper, more fundamental reality. In this view, our perception of three-dimensional space and time could be a digital illusion, akin to the way a 3D image is generated by a 2D surface in a hologram. This could be an indication that the cosmic bubble we inhabit is not as real as it seems, but is instead a sophisticated simulation, a projection of information encoded at a deeper level of reality. The cosmological implications of a simulated universe. If the simulation hypothesis is true, it has profound implications for our understanding of the cosmos and our place in it. The idea that we might be living inside a simulation challenges our assumptions about space-time, causality, and the very nature of existence. If our universe is a simulation, then the rules of physics, the constants of nature, and the events of history could all be controlled by an external force, a civilization or superintelligence that has created our simulated reality. One of the most fascinating aspects of the simulation hypothesis is the possibility that the creators of the simulation might have designed the universe with specific parameters in mind. Just as we simulate worlds in video games with certain rules and boundaries, the designers of our universe might have created a set of physical laws to see how life and consciousness would emerge in this artificial environment. This raises the question, if we are living inside a simulation, could the creators be monitoring us, or is the simulation entirely autonomous? This idea has led some thinkers to propose that our universe might be fine-tuned in a way that suggests it was designed for a purpose. The fine-tuning problem refers to the fact that the fundamental constants of nature, such as the strength of gravity or the charge of the electron, appear to be precisely calibrated to allow for the existence of life. If these constants were even slightly different, life as we know it would be impossible. Could this fine-tuning be evidence of a designer, an advanced civilization that created our simulation with specific parameters in mind? The simulation argument and the multiverse. If we accept the simulation hypothesis, it raises the intriguing possibility that our universe is just one simulation among many. This fits perfectly with the idea of a multiverse, in which there are countless universes, each with its own set of rules, laws, and parameters. If advanced civilizations are capable of creating simulations, they might create an infinite number of simulated universes, each one running different scenarios and experiments. In this scenario, the cosmic bubble theory and the multiverse hypothesis are not in conflict with the simulation argument. In fact, they complement each other. Each bubble universe could represent a different simulation, with its own set of rules and physical constants. Just as our universe might be a bubble within a larger multiverse, our simulation could be just one of many, each created for a different purpose or experiment. These simulations could be as varied as the Level 1, Level 2, Level 3, and Level 4 multiverses we discussed earlier, with each one having its own unique characteristics, structures, and inhabitants. How could we prove the simulation? Hypothesis. The question remains, how could we ever prove that we are living inside a simulation? Some scientists argue that we might never be able to detect the simulation because the very nature of our reality is based on the computational framework that we perceive as space and time. However, others suggest that there may be ways to test the simulation hypothesis. One possible method is to look for glitches or anomalies in the fabric of space-time. If the RFM universe is a simulation, there could be computational errors or limits to the resolution of the simulation. Just as a video game has a finite resolution, a simulation of the universe might have limits to how finely it can encode space and time. These glitches could appear as irregularities in the physical laws of nature or as anomalies in the cosmic microwave background radiation, quantum mechanics, or even the structure of space-time itself. Another approach might be to look for evidence of an external observer or creator. If we are living in a simulation, the creators might have left behind clues or signals, either in the form of mathematical patterns or cosmic events that are too precise to be the result of random processes. These signals could be hidden within the very fabric of the universe, waiting to be discovered by an advanced civilization capable of detecting them. Conclusion: is the universe a simulation? The possibility that we are living in a simulation is a deeply unsettling thought, but it is one that cannot be dismissed outright. While we currently have no direct evidence to support the simulation hypothesis, the concept challenges everything we think we know about reality, space-time, and the nature of existence. Whether we live inside a simulation or not, the idea forces us to ask profound questions about the nature of consciousness, the fine-tuning of the universe, and the limits of our understanding. In the context of the cosmic bubble theory and the multiverse, the simulation hypothesis adds a new layer of complexity. If our universe is indeed a simulation, it could be just one bubble in a vast, infinitely complex multiverse, created by an external force for reasons we may never fully understand. The search for answers to these questions is ongoing, and as our understanding of the universe deepens, we may one day discover whether we are living inside a simulation or whether our universe is truly the result of natural processes. For now, we can only continue to explore the mysteries of the cosmos, embracing the unknown and seeking the truth. As we delve deeper into the mysteries of the cosmos, the concept of the cosmic bubble brings with it not just philosophical musings, but profound implications for the future of space exploration. The idea that we could be living inside a bubble, an isolated, self-contained universe floating within an infinite multiverse, poses intriguing questions about the nature of space and time, the limits of our understanding, and more importantly, what lies beyond our observable universe. If our universe is indeed a bubble within a vast multiverse, then what awaits us on the other side of the bubble? And more pressing, how do we explore the boundaries of our cosmic bubble, given the limitations imposed by the vastness of space, time, and technology? In this chapter, we will explore the future of space exploration and the potential for discovering new frontiers beyond our bubble. Look at the possibilities for breaking through the boundaries of the observable universe, the challenges involved in such monumental exploration, and the potential technologies that could enable us to venture beyond the known universe. From missions to distant exoplanets to the possibility of traveling to the very edge of space-time itself, the future of space exploration promises to be one of the most exciting and transformative eras in human history. Breaking the boundaries of the observable universe. The observable universe is the region of space that we can currently detect and measure, limited by the speed of light and the age of the universe. The furthest objects we can observe are approximately 46 billion light-years away. And beyond this horizon lies an infinite expanse of space that is completely inaccessible to us. In essence, the observable universe is a bubble within a larger, unobservable cosmos. But what if we could somehow break through the boundaries of the observable universe and explore what lies beyond? The challenge of exploring beyond the observable universe is immense. As we discussed earlier, the expansion of the universe means that galaxies and cosmic structures are constantly moving away from us, and the light emitted by distant objects is increasingly redshifted, making it more difficult to detect. Additionally, as the universe continues to expand, regions of space will move farther and farther beyond the cosmic horizon, eventually becoming completely unreachable. However, the very concept of the cosmic bubble suggests that there could be limitless space beyond the observable universe. And while we may never be able to physically explore this vast unknown with current technologies, the idea of discovering what lies beyond the observable universe remains one of the most tantalizing goals for the future of space exploration. New technologies for exploring the edge of space-time. In order to explore the unknown regions beyond our cosmic bubble, humanity will need to develop entirely new technologies, ones that can overcome the immense challenges of space-time expansion, intergalactic distances, and the speed of light. As we look to the future, there are several promising technologies that could enable us to push the boundaries of space exploration and venture further into the cosmos. Faster-than-light travel. The quest for a warp drive. One of the most exciting possibilities for the future of space exploration is the concept of faster-than-light, FTL travel. For decades, the idea of traveling faster than light has been the stuff of science fiction, but recent breakthroughs in theoretical physics have suggested that FTL travel may not be entirely impossible. In 1994, physicist Miguel Alcubierre proposed the Alcubierre drive, a theoretical model for faster-than-light travel that uses a warp bubble to distort space-time. This concept relies on the idea that, while nothing can travel faster than light within space, space itself can expand or contract at speeds exceeding the speed of light. The Alcubierre drive involves creating a bubble of space-time that moves faster than light, carrying a spacecraft inside it. The ship itself would not be moving within the bubble, but rather, the bubble would move through space-time, allowing the spacecraft to travel faster than light without violating the laws of physics. While the Alcubierre drive remains purely theoretical and faces immense technological challenges, such as the need for exotic matter with negative energy, it offers a tantalizing glimpse into the future of space exploration. If developed, such a technology could allow us to break free from the limitations of the observable universe and explore regions of space that are currently beyond our reach. Wormholes, shortcuts, through space-time. Another theoretical possibility for faster-than-light travel is the concept of wormholes, shortcuts through space-time that connect distant points in the universe. Wormholes are a prediction of Einstein's general theory of relativity, which describes how gravity bends space-time. A wormhole is essentially a tunnel that connects two separate points in space-time, allowing for instantaneous travel between them. While wormholes are fascinating in theory, they also come with significant challenges. To create a stable wormhole, enormous amounts of energy would be required to keep it open, and the structure of the wormhole itself could be highly unstable. There are also questions about the nature of the material that would be required to stabilize the wormhole, as well as the potential dangers of traveling through such a cosmic tunnel. Despite these challenges, wormholes remain one of the most intriguing possibilities for intergalactic travel. If we were able to harness the power of wormholes, we could theoretically travel to distant galaxies and even other universes within a matter of moments, bypassing the limitations of light-speed travel and allowing us to explore the farthest reaches of the cosmos. Quantum propulsion and the future of space travel. In addition to FTL travel and wormholes, quantum propulsion is another emerging concept that could revolutionize space exploration. Quantum propulsion involves using the principles of quantum mechanics to generate thrust and move a spacecraft through space. One potential approach is the M-drive, a type of electromagnetic drive that purportedly generates thrust without the need for fuel or propellant. Although the M-drive remains highly controversial, with some researchers questioning its viability and the underlying physics, the concept of quantum propulsion is an exciting area of research. If successful, quantum propulsion could provide a way to explore distant stars and galaxies without the need for traditional rocket fuel, making interstellar travel much more feasible. The search for exoplanets, finding other bubbles in the multiverse. While the idea of traveling beyond the observable universe is still far from reality, one of the most exciting areas of space exploration in the coming decades will be the search for exoplanets, planets that orbit stars outside of our solar system. As of now, scientists have discovered thousands of exoplanets, and many of these worlds exist in the habitable zone of their stars, where conditions might allow for liquid water and, potentially, life. The discovery of Earth-like exoplanets has opened up new possibilities for the future of space exploration. One of the key goals for the coming decades will be to identify planets that are similar to Earth and could support life. The James Webb Space Telescope, JWST, set to launch in 2021, will be able to study the atmospheres of exoplanets in unprecedented detail, looking for signs of water, oxygen, methane, and other potential biosignatures that could indicate the presence of life. The discovery of habitable exoplanets is not only important for understanding the potential for life beyond Earth, but it could also offer insight into the possibility of other bubbles in the multiverse. If our universe is one of many bubble universes, the search for exoplanets could help us understand how other bubble universes might form and what their characteristics might be. Perhaps one day, we will find a planet that is home to intelligent life, perhaps even life that is as curious about the universe as we are. Beyond our solar system, missions to other stars. While exploring exoplanets is a crucial goal, another significant frontier in space exploration is the possibility of traveling beyond our own solar system. Missions to other stars are still in the distant future, but there are several exciting projects that are paving the way for interstellar exploration. One such project is Breakthrough Starshot, a plan to send tiny, lightweight spacecraft to the nearest star system, Alpha Centauri, using laser propulsion. The goal of Breakthrough Starshot is to launch a fleet of small, sail-like spacecraft that would travel at a fraction of the speed of light, reaching Alpha Centauri in just over 20 years. While this mission is still in its early stages, it represents the first serious effort to send probes to other star systems, and it could open up new possibilities for exploring other stars and planets. Missions like Breakthrough Starshot could also provide valuable insights into the nature of space-time and the limits of the cosmic bubble. As we explore distant star systems, we may discover more about the boundaries of our universe, the forces that govern its expansion, and the potential for life beyond Earth. These missions could be the first steps in understanding whether our bubble universe is unique or just one of many in a larger multiverse. Conclusion: the infinite possibilities of exploration. The future of space exploration is one of limitless possibilities. Whether we are breaking through the boundaries of the observable universe, traveling to distant exoplanets, or attempting to explore the outer reaches of space-time, the potential for discovery is vast. As we develop new technologies, new theories, and new missions, we will continue to push the boundaries of what's possible. The idea of living inside a cosmic bubble raises profound questions about the nature of space, time, and reality. While we may never be able to explore the multiverse or travel beyond our cosmic bubble, the journey of exploration itself will continue to shape the future of science, technology, and human knowledge. The unknown awaits, and with every new discovery, we come one step closer to understanding the true nature of the universe. As we reach the final chapter of our exploration into the concept of the cosmic bubble, the multiverse, and the deep mysteries of the universe, we are left with a profound realization. The universe is far more mysterious and complex than we could have ever imagined. The questions we've raised throughout this journey, the nature of space-time, the possibility of cosmic bubbles, the role of dark matter and dark energy, and the existence of multiple universes, represent only the beginning of our quest for understanding. The deeper we look into the cosmos, the more we realize how much we don't know, and that is what makes the exploration of space so endlessly fascinating. Throughout this exploration, we've uncovered radical new ways of thinking about the universe, ways that challenge our assumptions and force us to reconsider what we thought we knew. The idea that we could be living inside a cosmic bubble is just one such idea, but it opens the door to new possibilities and new understandings. And while we may never fully grasp the ultimate truth of our existence, the pursuit of these questions will continue to drive scientific discovery for generations to come. In this final chapter, we will reflect on the journey we've taken, the questions that still remain unanswered, and the importance of curiosity and exploration in shaping our future. The mysteries of the universe may be vast and complex, but it is this very mystery that fuels our drive to explore, to discover, and to learn. We are on the brink of a new era of space exploration, one that promises to expand our understanding of the cosmos in ways we can only begin to imagine. And as we look to the future, we must embrace the unknown, not as a challenge to be feared, but as an opportunity to expand the boundaries of human knowledge and experience. A universe full of questions. The exploration of the cosmos has always been driven by one fundamental question: what lies beyond our understanding? From ancient civilizations looking up at the stars to modern scientists peering into the depths of space, humans have always sought to understand the nature of the universe and our place within it. Over the centuries, we've developed increasingly sophisticated tools and theories to answer these questions, but with each new discovery, we find that the universe is even more complex and mysterious than we could have imagined. The cosmic bubble theory is just one example of how our understanding of the universe continues to evolve. Once, we believed the universe was infinite and unbounded, but the idea of a bubble universe challenges this notion, suggesting that space-time could be finite, and our universe might be part of a larger, more complex structure. This radical shift in thinking has opened the door to new theories and new possibilities, from the multiverse theory to the idea of living in a simulation. But for every answer we uncover, more questions arise. If our universe is a bubble, what lies beyond its boundaries? If the multiverse exists, how do we connect with other universes, if at all? What is the true nature of dark matter and dark energy? And how do these hidden forces shape the cosmos? And perhaps most fundamentally, what is the true purpose of the universe, if there is one? These questions, while not easily answered, are at the heart of scientific discovery. The more we learn, the more we realize that the cosmos is full of profound mysteries, mysteries that challenge the limits of our understanding and stretch the boundaries of human imagination. And it is this pursuit of knowledge, this willingness to question and explore, that drives the future of science and space exploration. The role of curiosity and exploration. Human curiosity is one of our most defining traits. From our early ancestors using primitive tools to investigate the natural world, to the exploration of the heavens with telescopes and spacecraft, curiosity has always been the driving force behind our quest for knowledge. It is this insatiable desire to know and understand that has led us to develop technologies that allow us to peer into the depths of space, discover exoplanets light years away, and even imagine the possibility of life beyond Earth. The pursuit of space exploration is, at its core, about answering the big questions, the ones that go beyond mere curiosity about our immediate surroundings. We want to know where we came from, how the universe began, and whether we are truly alone in the cosmos. But space exploration is not just about finding answers. It's also about asking better questions and discovering new possibilities we hadn't even considered. The very idea of the cosmic bubble theory is a product of human curiosity. The concept that we might live in a finite, self-contained universe, surrounded by an infinite multiverse, challenges our assumptions about space and time. It forces us to rethink what we know about the cosmos and opens up a whole new frontier of questions to explore. Could our universe be part of a much larger, infinite collection of universes, each with its own distinct laws of physics? What would it mean to exist in such a vast, interconnected multiverse? The future of space exploration lies in embracing this curiosity, in questioning the status quo, and in pushing the boundaries of what we think is possible. It is through exploration that we discover not just new facts, but new ways of thinking, new paradigms that can fundamentally alter the course of human knowledge. The future of space. Exploration, a new era of discovery. As we look to the future, we stand on the brink of a new era in space exploration. The advancements in technology and the growth of private space companies like SpaceX, Blue Origin, and Virgin Galactic are revolutionizing the way we approach space travel. These companies are developing spacecraft that could allow us to travel further and faster than ever before, potentially opening up new frontiers of exploration in the solar system and beyond. One of the most exciting prospects for the future of space exploration is the possibility of human colonization of Mars. In the coming decades, NASA and private companies are working to make this dream a reality. Mars, with its relatively Earth-like conditions, is seen as the best candidate for human settlement. Establishing a permanent presence on Mars would mark a major milestone in our efforts to become a multiplanetary species, ensuring the survival of humanity in the event of catastrophic events on Earth. But the possibilities don't end with Mars. As we develop more advanced propulsion technologies and explore the outer planets and moons of our solar system, we may one day find ourselves traveling to distant stars and exoplanets. The James Webb Space Telescope, set to launch in 2021, will provide us with unprecedented views of distant planets, and missions like Breakthrough Starshot could one day send probes to nearby star systems like Alpha Centauri. Beyond our solar system, the search for habitable exoplanets will continue to be a major focus. The discovery of Earth-like planets in the habitable zone of other stars is one of the most exciting developments in modern astronomy. Could there be other worlds out there, similar to ours, where life exists? And if so, what does that mean for our understanding of life in the universe? As we venture farther into space, we will continue to encounter new mysteries, some we can predict, and others that will challenge our wildest imaginings. The exploration of the universe is a never-ending journey, one that will continue to expand our understanding of the cosmos and our place within it. Embracing the unknown, the key to progress. As we've seen throughout this exploration of the cosmic bubble theory, the multiverse, and the future of space exploration, the key to unlocking the deepest secrets of the universe lies in embracing the unknown. The universe is vast and filled with mysteries, many of which we are only beginning to comprehend. Whether we are exploring the boundaries of the observable universe, seeking life on distant exoplanets, or uncovering the fundamental forces of dark matter and dark energy, each discovery leads us to more questions, more challenges, and more opportunities for growth. In many ways, the unknown is what makes space exploration so exciting. It is the very mystery of the cosmos that drives us to venture beyond the limits of our current knowledge. It challenges us to think bigger, to imagine possibilities we have never considered, and to push the boundaries of what we think is achievable. The unknown is not something to fear. It is an opportunity to expand the limits of human knowledge and experience, and it is this pursuit of discovery that will continue to define the future of space exploration. The future of space exploration is not just about discovering new planets, galaxies, and phenomena. It is about redefining our understanding of the universe itself. The cosmic bubble theory, the multiverse, and the exploration of dark matter and dark energy all point to the same fundamental truth. The universe is far stranger, more complex, and more interconnected than we ever imagined. Conclusion: the endless journey. As we conclude this exploration of the cosmic bubble theory and the future of space exploration, we are left with one undeniable truth. The universe is full of possibilities, and our journey of discovery has only just begun. Whether we are living inside a bubble, part of an infinite multiverse, or simply scratching the surface of a much larger reality, the pursuit of knowledge will continue to shape our future. As we venture into the unknown, we are reminded that the journey itself is just as important as the destination. Every discovery, every new theory, and every new piece of data brings us closer to understanding the nature of the cosmos and our place in it. And with each new breakthrough, we come one step closer to unlocking the deepest mysteries of the universe. So, as we look to the stars and imagine what lies beyond our cosmic bubble, we must embrace the unknown, not as something to be feared, but as something to be explored. For in the vast, infinite cosmos, the possibilities are endless, and our journey has only just begun.